Hello everyone, I'm Christina and welcome to video 8 of our A-Level Mathematics Calculus series. In this video we are finishing off differentiating trig functions from first principles, and we will be looking at the derivative of tan x from first principles in this video. I'm also going to state the small angle approximation for tan x, which we get from our small angle approximations for cos and sine, which we looked at in the previous video. So we know that our f of x in finding the derivative of tan x from first principles is tan x. And I've written down the expression for the derivative from first principles on the right here. So what we need to find next is f of x plus h to use for our expression. And we will find that by substituting in x plus h into our function here. So we're looking for tan of x plus h. Now, if we think back to our trig series videos, then we can recall that tan of a plus b, that's our tan double angle formula, equals tan a plus tan b all over 1 minus tan a tan b. So then if we want tan of x plus h, using our double angle formula for tan here, we can rewrite this as tan of x plus tan h all over 1 minus tan x tan h. Okay, so now we can use this expression in our expression for the derivative f dash of x. So then we can write f dash of x equal to the limit as h tends to 0 of f of x plus h, but we just found that to be this expression here. So tan x plus tan h over 1 minus tan x tan h minus tan of x, which is our f of x. Label it clearly here. This is for f of x plus h, and this is our f of x. And that is all over h. So the first thing we might want to do is to try and combine the two terms that we have in the numerator into one term. And we need to do that by making the denominators the same and combining these fractions. So if we think of tan x as being over 1, we know that if we want to make the denominators the same, it will be easiest to multiply 1 minus tan x tan h. Sorry, it'll be easier to multiply the denominator of our expression here by 1 minus tan x tan h. So if I write that out, so f dash x equals the limit as h tends to 0. Now, that first term is going to stay the same. 1 minus tan x tan h. But then I want to multiply the fraction on the right by 1 minus tan x tan h, so I can make the denominators the same. So that's going to give me tan x multiplied by 1 minus tan x tan h over 1 minus tan x tan h all over h. So now, because the denominators are the same for these two fractions, we can combine the numerators. So if I do that first, that means I'm combining tan x plus tan h and taking away tan x times 1 minus tan x tan h. So if I first multiply out the term on the right first, I'll get tan x minus tan squared x tan h. And then, of course, the term on the left here is just tan x plus tan h all over 1 minus tan x tan h. And we can write that because the denominators are the same and we're combining them into one fraction. And that's going to be all over h. So if I'm dividing this fraction that I have here by h, then the h ends up in the denominator here. Okay? And then I can just complete that by writing f dash of x as the limit h, the limit of h tending to 0. So now we can try and clean this up. F dash of x is the limit h tends to 0. We can see up here that this tan x is going to cancel with this tan x because we have tan x minus tan x. So that, you can already see that disappears. And then what do we have left? We have tan h in the numerator minus tan squared x tan h. That's going to be plus tan squared x tan h all over h1 minus tan x tan h. So now we're a little bit stuck. What we need to do is apply our small angle approximation for tan. So if we write out here our small angle approximation for tan x. So recall that the sin x approximates to x for very small values of x or very small angles, and we write it as x being much less than 1. And cos x approximates to 1 for x, very small values of x, and we write that as x being much less than 1. And so what do we approximate tan x to? Well, that's going to be small angle approximation of sin x over cos x. And so that approximates to x over 1, which is just x, for x much less than 1. So these two are from our previous video. And we can see exactly how we get the small angle approximation for tan x from sin x and cos x. Okay? So using that result now, we can rewrite f dash of x, limit as h tends to 0 of our expression here. Well, we can see using our small angle approximation that tan of h, that we can apply the small angle approximation by saying tan of h approximates to h, because remember h is tending to 0, so h is very small. So we're left with h plus tan squared x times tan h. Again, tan h approximates to h, so we can write h plus h tan squared x in the numerator all over h 1 bracket 1 minus tan x, and then again tan h here also approximates to h. We can write the h there. Now the easiest thing to see here is that in the numerator we can take out a factor of h, and if we do that, I'll write it here. We take out a factor of h, we're left with 1 plus tan squared x all over h 1 minus h tan x in brackets there. So the h in the top cancels the h bottom of the fraction there. And then what we're left with, I'll write it below our small angle approximation, is f dash of x, limit as h tends to 0 of 1 plus tan squared x over 1 minus h tan x. But of course, h is tending to 0, so this term here actually goes to 0. And so what we're left with ultimately is 1 plus tan squared x over 1. So we can just write that as 1 plus tan squared x. But if we think back to one of our first trig videos, we know that 1 plus tan squared x is actually equal to sec squared x from our trig series. So 1 plus tan squared x equals sec squared x, which you can also write as 1 over cos squared x, because it's one of our reciprocal trig functions. So to summarize here, for f of x equal to tan x, the derivative of tan x, f dash of x, is equal to sec squared x, or 1 over cos squared x.